Okay, let's continue the class. Thank you all for mentioning the solutions. About closing the microphone. I will study it myself. I guess I can do it on OBS. As the classmate said. I'm not so familiar with OBS. I will practice OBS myself. Some classmates asked. Good questions in the chat room. These two questions are the same. In the first question, he said. We have one S and one A in pair. If we don't want the actor takes A. What action does the actor take? Does the actor do nothing? So, that the actor doesn't take action A means that it can do any other things. Doing nothing, for an actor, is also an action. If you want the actor to have the opportunity to do nothing, then doing nothing is also an action. There are three actions in Space Invaders: to fire, to go left, and to go right. Suppose you want your actor has another possible action where the actor doesn't choose any of the three actions but stay. You should add stay into the possible choices for actor. That the actor doesn't take action A means that it can do any other things. For example, you don't want your spaceship to go left. It can either fire or go right. Okay, here's the second question. Given S, can we decide one desired action A and another undesired action A prime? Yes, you can. Given one observation. You want your actor to choose to fire, but not to go right. Then, to fire will have a high score. To go right will have a low score. The actor wants to fire, but not to go right. Actions are sampled randomly. Given observation. The decision may not be the same every time. The randomness of sampling make decisions different. The score of these actions will determine the probability of its appearance. If you want your actor to choose to fire, but not to go right, just give the action to fire a higher score. To fire will have a higher probability to be sampled, and to go right will have a lower probability. There is another question. Actor will have a positive score if it does A1. If you want to maximize the scores of all actions, why don't add a negative sign to the loss function? Let me take a look. The actor takes the action A1. Will have a positive score. If you want to maximize the scores of all actions, why don't you add a negative sign? Sorry, I didn't understand your question. I don't understand the problem. We are not trying to maximize the scores of all actions. What we want to maximize is the total reward. After one episode, we can get the reward of each action. Sum up rewards from each action. Then we can get the total reward. Maybe I don't answer your question correctly. If you still have questions, you can try to express your question in another way. I will answer your question if I can. Okay. Let's continue the class. So far, you might think there is no difference between supervised learning and reinforcement learning. That is indeed no difference. The next key point is how we define A. How to define A. Let me talk about the simplest but incorrect version first. This one is actually the version that teaching assistant sample code adopts. How exactly did we do it in the incorrect version? This incorrect version looks something like this. First of all, we still need to collect some training data, which are SA pairs. How do we collect these pairs? We need to have an actor that interacts with the environment. This way, it can collect SA pairs. Where did the actor come from? You may find it a bit odd, since the goal of this task was to train an actor. However, we need to have an actor to interact with the environment and record the S and A of the actor. Where did we get the actor from? For now, treat the actor as something random. The initial actor is just a random thing. When it sees S1, the action it performs makes no sense, or at random, so to speak. But we will record every A that it performs at each S. Usually, when we're collecting data, We won't only make one episode of the actor and the environment. We usually make multiple episodes, in hope of collecting enough data. For instance, there are 5 episodes in the sample code to collect enough data. Now, we go and observe an actor and see how it interacts with the environment. We then record the actions the actor performs from each observation and use it to evaluate each action and whether it's a good move or a bad move. After the evaluation, we can take the result of our evaluation to train the actor. How do we evaluate? We've mentioned that we will use A to evaluate each step and whether we hope the actor to take a certain action or not. Here's the easiest way to do evaluations. Assume that we executed A1 in a certain step S1 and got reward R1. If the reward was positive, perhaps it means that the action is a good one. If the reward is negative, perhaps it means that the action is a bad one. So, we treat R1, R2, which are the rewards, as A. A1 is R1, A2 is R2, A3 is R3, and AN is Rn. This would be equivalent to telling the machine that A1 is a good action, and we should execute A1 every time we encounter S1. Because we got a positive reward by executing A1. If you execute A2 when we encountered S2 and got a negative reward, it means that A2 is a bad move, and we should not execute A2 next time we see S2. Now, the version 0 we're talking about was not a good version. Why is it not a good version? Because, if you use this method and set A1 to R1 and A2 to R2, the network trained by this method would create a short-sighted actor. It would be an actor that has no concept of long-range planning at all. Why's that? We know that every action would affect future interactions. In other words, the actor executing A1 in S1 and getting R1 do not represent the whole interaction. Because selecting action A1 affect the S2 we'll see in the future. S2 will affect the next action, A2, and also affect the next reward, R2. So, A1 will also affect whether we will get R2 or not. So, each action is not independent. Every action will affect what happens next. Okay, when we are interacting with the environment, there is a problem called reward delay. What is reward delay? Sometimes, you need to sacrifice short-term benefits in exchange for a longer-term goal. Assuming you are playing Go. If you watched Demi-Gods and Semi-Devils, you would know that Xu Zhu cracked Zhen Long's Go game by sacrificing one play, which reduces a lot of advantages temporarily. But, in the end, he won the game. A similar play in the game of Space Invaders may be like that. You may need to move left and right to target on, and then shoot to get points. For moving left and right, there is no reward. The reward obtained by moving left and right is 0. Only shooting will give you reward. But it doesn't mean that moving left and right is not important. We will need first to move left and right to find the target. And then our shooting will be effective. So, sometimes we will need to sacrifice some short-term rewards in exchange for a long-term reward. So, assuming that we use version 0, what will it happen? From the perspective of the machine, as long as it takes left and right, the reward it gets will always be 0. If the machine chooses to fire, the reward it gets will be positive. Only when firing will the entailing reward be positive. The reward will be positive only when machine fires. Then, machine will learn that only firing madly is correct, because only firing could give it positive rewards. Any other behaviors will not receive any reward. So, any other behaviors are not encouraged, and only firing is encouraged. Version 0 will let it learn to only madly fire. Version 0 is used in the sample code from TA. Of course, this is also executable. It's just that the results won't be good. The reason why TA adopted version 0 is that somehow, this version 0 for everyone seems to be a common mistake. While implementing reinforcement learning. While implementing, you are prone to take version 0 directly and get a bad result. What should we do to avoid this issue? So now, we start to officially introduce reinforcement learning. We will take a look at how policy gradient works. So, we need to have a new version 1. Fortunately, in version 1, how good A1 is doesn't depend on R1. It depends on everything that happens after A1. We will first execute A1 and collect all the rewards from R1, R2, R3, to Rn, and sum them up to get a value called G1. Then, we will say that A1 is equal to G1. We use this G1 as a metric for evaluating whether an action is good or not. Previously, we used R1 to evaluate directly. Now, it is not. We take G1 to evaluate. Then, we add up all the following R to evaluate the action A1. Because, after we execute A1, a series of things, like these, happen. Adding up those series of things, we may be able to evaluate A1 to know whether it is a good action or not. And so on. How good is A2? After executing A2, we add up all the following R from R2 to Rn to evaluate the G2. Then how good is A3? After executing A3, we add up all R and get G3. So we add up all those things. We call G as the cumulated reward, adding up all future rewards to evaluate the quality of an action. Sounds much more reasonable. So this G is the cumulated reward. What is GT? Starting from the time point t, we add from RT to Rn. All together is the cumulated reward GT. Then we use this cumulated reward to evaluate the quality of an action. When we use cumulated reward, we solve the problems encountered in the version 0. Because you may move to the right, then aim, fire, and hit the aliens. Then the action, move to the right, also has cumulated reward. Although there is no immediate reward for moving to the right. Suppose A1 is move to the right. Then R1 may be 0. But this action might lead to aiming and caused aliens to be killed. Hence, the cumulated reward will be positive. Then we will know that moving to the right is also a good action. This is version 1. But if you think more thoroughly, you will find out that version 1 seems to have some problems. What's the problem? Assume that the game lasts very long. It seems inappropriate that you attribute Rn to A1. That is, when we take the behavior of A1, the immediate impact is R1, and then affect R2, and then affect R3. If this process is very, very long, then we say that A1 results in Rn. This possibility should be very low. Maybe the credit for Rn should not be attributed to A1. How to solve it? There is a second version of cumulated reward. We use G' to denote the cumulated reward. We will multiply a discount factor in front of R. This discount factor gamma is a value less than 1. May we set gamma to like 0.9 or 0.99. So what is the difference between this G1' and G1? G1 equals to R1 plus R2 plus R3. What about G1'? G1' is R1 plus gamma times R2 plus gamma squared times R3. The farther away from taking this action, the more power of gamma it have. So R2 is 1 step away from A1. We just multiply gamma. R3 is 2 steps away from A1. We multiply gamma squared. When we finally get to Rn, Rn has almost no influence on G1', because gamma is multiplied many times, where gamma is a value less than 1. Even if you set 0.9, 0.9 to the power of 10 is very small. With this method, the rewards that are closer to A1 gain more weight. Those rewards far away from me gain a smaller weight. So we now have a new A. This new A, this assessment of action, can be represented by G1'. Then its formula can be written like this. GT' is the summation over n from t to the capital N. Then we multiply Rn by gamma to the power of nt. So for the reward far away from the action, its gamma is multiplied many times, thus having less effect on G prime. This is the second version. Do you think it makes more sense? Okay, let's see if you have any questions to ask. Some classmates said that it is similar to Monte Carlo. Great. I'll talk about Monte Carlo later. Here is a question. Is a brace an episode? Or is this blue brace an episode? Well, a brace is not an episode. A brace is an observation. When executing this action, this is a piece of data. It is not an episode. An episode consists of many observations, combined with many actions. Here is one more question. Does G1 need to be normalized? It is a great question. Why? Because it is version 3. Okay, let's continue to talk about version 3. Here is another problem. Do the earlier actions accumulate more points? And the later action accumulate fewer points? Yes. It is correct. Indeed. However, that the earlier actions accumulate more points can also be a reasonable situation. Think about it. Those earlier actions have a greater impact to the latter ones. At the end of the game, there are no aliens to kill. What you might do has little impact on the result. So the actions of the earlier observation are something we may need to pay special attention to. But how to decide like this kind of a? There are many different methods. If you don't want the earlier action to have a larger weight, you can completely change the definition of A. In fact, different RL methods have different ways to define A. It still seems not suitable for games like Go. After all, a game like Go only has a score at the end. Okay, this is a good question. Can the methods we are talking about handle the kind of game with a score at the end? It's not impossible, right? Actually, it is still possible. How? Assuming that the only Rn has a score. Everything else is 0. What will happen? After taking a series of actions, as long as you win in the end, this series of actions are all good. If you lose, this series of actions are all bad. And you might feel like doing so will be difficult to train the network. It's really hard to train. But as far as I know, the earliest version of AlphaGo is trained by this method. It's amazing. It actually did so. It used such technology. Of course, along with some other methods. For example, value network, etc. I'll talk about it later. The earliest AlphaGo has adopted this kind of technology to do learning. It has tried to adopt such a technique and seems to be able to learn. Take the estimated error as the reward. A classmate said that it is in fact AlphaGo. You can use the estimated error as a reward. However, you have to have a way to estimate the error first. Then you can use it as the reward. So is there any way to estimate in advance? How much reward will we get next? Yes, in the later version. There will be such a technology. But I haven't talked about that one yet. Okay, let's talk about the version 3 next. Version 3 is just like what the classmate asked. Do we need to normalize it? Yes. Then why? Because good or bad is relative. Good or bad is relative. Why is good or bad relative? Suppose today in this game, every time you take an action, the lowest score is preset to 10 points. Then getting a reward of 10 points is actually very bad. It's like saying that today you said you got 60 points in a certain course. Is it good or bad? Is it bad? Nobody knows. Because it depends on how many points others get. If everyone else get 40 points, you get the highest score in the class. Then you are great. If everyone else get 80 points, then you have the lowest score in the class. That's not great. So reward is relative. So if we simply calculate G, we may encounter a problem. Suppose in this game, we always get a positive score. Every action will give us a positive score. It's just that there are big and small scores. Then your G will be all positive when you calculate in the old way. Some behaviors are actually bad, but you will still encourage your model to take these actions. So what to do? We need to standardize. Let me talk about the easiest way here. We subtract a, b, from all G. This b is usually called baseline in the literature of RL. This is a bit different from the baseline of our homework. But anyway, in the literature of RL, it's called baseline. We subtract ab from all G prime. The goal is to make some G prime positive and some negative. For very high G prime, makes it positive. For very low G prime, makes it negative. Okay, but there will be a problem here. How to set this baseline? How do we set a good baseline to let G prime be positive and negative? We will mention it again in the next version. But now we stop here. Okay, a classmate said that we might need a better heuristic function. Yes, we need one. When playing Go, supposing today your reward is very sparse, then you may need a good heuristic function. If you have seen the most earlier, the deep blue paper, which before the machine has beaten humans in Go, it has already beaten humans in chess. That's called deep blue. Deep blue has a lot of heuristic functions. It's not just getting rewards at the end of the game. There will be many situations that it will get rewards in the middle of the game. Okay, what I just talked about is the overall concept. Then I will actually tell you. How does policy gradient work? Then you can read the TA's sample code carefully. That's the algorithm in the sample code. First you have to initialize randomly. Initialize your actor randomly. You just give your actor a randomly initialized parameters. That's call it theta 0. Then next, you enter your training iteration. Suppose you want to run T training iterations. Okay, then you take your current actor to interact. At the beginning, this theta 0 was stupid, it knows nothing. It randomly takes actions. But it will get better. You take your actor to interact with the environment. And then you get a lot of S and A. You get many S and A. And record the process of these interactions. After getting these S and A, you have to evaluate them. You use A1 to AN to decide whether these actions are good or not. You take your actor to interact with the environment and collect these observations. Next, you have to evaluate them. See if these actions are good or not. What you really need to care about, or what you need to change, is the process of evaluating. In the TA's code, this A is directly set to the immediate reward. You have to change this part to get good results. After setting this up properly, it's over. You just define the loss and update your model. The update process is the same as the gradient descent. It will calculate the gradient of L multiplied by the learning rate. Then, take this gradient to update your model. Update theta I minus 1 to theta I. But there is a magical thing here. In general training methods, or the training methods we have learned so far, data collection is outside the for loop. For example, I have a bunch of data, and use this bunch of data for training and updating the model many times. Finally, you can get a converged parameters, and use these parameters for testing. But the flow in RL is not the same. You can find that the data collection is in the for loop. Suppose you plan to run 400 times. In this for loop, you have to collect data 400 times. Or, we use a graphical way to represent it. This is the data you collected. You observe a certain actor, and the actions it executes in each state. And then you give an evaluation. As for what evaluation is used, it is up to you. You use the evaluation to judge whether the action is good or not. After you have these data and evaluations, you can take them to train your actor. You can use these evaluations to define a loss. Then, you can update your parameters once. But the interesting part is that you can only update once. Once the parameters are updated, you have to collect data again. After updating the parameters once, you have to collect data again to update the parameters for the next time. So, this is why RL takes a lot of time. During the training process, the process of data collection is in the for loop. After you update the parameters, your data will be collected again to update the parameters. After the update process is completed, you need to collect data again. If your parameters need to be updated 400 times, you need to collect data 400 times. This process takes a lot of time. You will ask, why it is like this? Why can't we have a single set of data to update the model 400 times? Why do we need to collect data again every time we update our model parameter? A simpler analogy here is that someone's food may be another person's poison. These data are collected by theta I-1. This is the result of theta I-1 interacting with the environment. This is the experience of theta I-1. These experiences can be used to update theta I-1. It can be used to update the parameters of theta I-1. But it is not necessarily suitable to update the parameters of theta I. Or let us see a particular example. This example comes from the 8th episode of Hikaru no Go. I believe everyone has seen it. I shouldn't need to explain the plot. This is Hikaru Shindo. He is playing chess with Sai. Here, Hikaru Shindo plays kogema. What exactly does kogema mean? I'm not very sure. But here is an explanation. Placing a go stone diagonally in a square is called kogema. Placing a go stone a few squares diagonally is called ogema. Okay, after playing the move, Sai says don't play kogema at this time. Ogema is better. Then Hikaru says, why ogema? I think kogema is also good. Sai explains. If ogema has 100 possibilities, then kogema has only 99 possibilities. Here comes the key point. It's right to play kogema before, because the moves after kogema are easier to predict and less error-prone. Moves after ogema will be more complicated, but if Hikaru wants to become stronger, he should learn to play ogema. Or after Hikaru became stronger, he should play ogema. So you see that the same move, which is playing kogema, have different effects for Go players of different level of skills. For the weaker Hikaru, it's right to play kogema, because he is less likely to make mistakes. But for a stronger Hikaru, it's better to play ogema. It becomes bad to play kogema. So the same action, the same behavior. For different actors, its outcome is not the same. So suppose we use theta I-1 to collected a bunch of data. These are the trajectory of theta I-1. These data can only be used to train theta I-1. You can't use these data to train theta I. Why can't we use these data to train theta I? Because even if theta I-1 and theta I in S1 both take A1, they may act differently at S2. So if theta I uses the trajectory of theta I-1, the trajectory that theta I-1 will execute is totally different from theta I. So it is inappropriate. If you take theta I-1 and the reward it gets to, evaluate the reward that theta I will get. So if we go back to the example of Hikaru no Go, assume that this A1 is kogema. Before Hikaru becomes stronger, this is a suitable way. But for Hikaru after becoming stronger, it may not be a proper move. So when we are collecting data to train your actor, you have to pay attention to whether the actor who collected the data is the same as the actor being trained. When your actor is updated, you'd better go ahead and collect data again. This is why gradient descent takes so much time. Okay, let's see if anyone has any questions. Let's see. First hand Tengen 5-5. Very good. In fact, you have to play 5 of 5 first hand. Second hand Tengen. Third hand 5 of 5. Then everyone will be very surprised. Okay, if you don't have any questions for now, then we'll continue. We said that the actor to be trained should be the same as the actor that interacts with the environment. When the actor we trained is the same as the interacting actor, it's called on-policy learning. The one we just demonstrated. The entire algorithm of policy gradient is on policy learning. There's also off-policy learning. We will not go into the details today. The main idea of off-policy learning is, can we separate the actor which is being trained and the actor that interacts with the environment? Can we train the actor with the experience of other actors interacting with the environment? There are lots of advantages to do off-policy learning. In the previous case, I just told you that theta I-1 cannot be used to train theta I if you are learning on policy. But there exist special methods using off-policy learning, which can make use of the data collected by theta I-1 to train theta I. Although theta I and theta I-1 are not the same, but some methods allow us to utilize the interaction data generated by theta I-1 to train theta I. The advantage is that you don't have to keep collecting data. One of the difficulties of reinforcement learning is that you need to collect data every time you update the parameters. As you can see, TA's demonstration updated the parameters 400 times. 400 times is not a lot, but it is a lot compared to the networks you've trained before. Wouldn't it be great if the data we collected can be used to update parameters multiple times? This is one of the off-policy learning's great advantages. But we won't go into the details of how off-policy learning is implemented. One classic method is called proximal policy optimization. Its abbreviation is PPO. It is commonly used method. It remains a strong method until now. So the most important point of off-policy learning is that the network must consciously recognize that it is different from the actor to interact. I won't go into the details today. I've left a link to the recording of the class before. You can study PPO by yourself if you are interested. Here is an analogy if you like. Imagine you are asking Chris Ivan, the Captain America, how to pursue a girl. Chris Ivan will show you how to do it. He is the actor to interact. He is the actor responsible for demonstrating. He said he has never failed if he confess his feelings to a girl. But you have to recognize that you are not Chris Ivan. Handsome people eat grass and ugly people. Oh, sorry. Handsome people eat grape and ugly people eat grass. You are different from Chris Ivan. So you might not be able to use the tricks Chris uses. You might have to change a little bit. This is the spirit of off-policy learning. The actor to train has to understand that the actor to interact is different from itself. So some of the data given by the actor to interact can be adopted, while some may not. For the details, here are some recordings you can listen to if you want to learn more. Here we have another very important concept called exploration. What does exploration mean? We have just talked about how the actor works. Today, when our actor takes an action, it has some randomness. And this randomness is in fact very important. Most of the time, if the degree of randomness is not enough, you will not be able to train. Why? I'll give the simplest example here. Assume that your initial actor always moves to the right. It never knows to fire. If it has never taken the action of firing, you never know about firing. Is it good or not? Only when the actor tries to fire and get a reward from firing will you have a way to evaluate whether this behavior is good or bad. Suppose there are some actions that have never been executed. Then you have no way of knowing whether this action is good or bad. So during training, the randomness of the actor used to interact with the environment is very important. You will expect the actor that interacts with the environment to be more random, so that we can collect more data. Then, there won't be the case that the rewards of some situations are never known. In order to make this actor more random, when you are training, you will deliberately increase its randomness. For example, the actor's output is a distribution. Someone will deliberately increase the entropy of the distribution, which makes it easier to sample the behaviors that have a lower probability during training. Or someone will directly add noise to the actor's parameters. Directly adding artificial noise to the actor's parameters can let the actor behave differently every time. Okay, this is exploration. Exploration is also a very important technique in the process of training RL. If you don't let the network try different actions during training, You are very likely to produce bad results. Okay, let's take a look. In fact, for this PPO method, DeepMind and OpenAI both propose the idea of PPO at the same time. Let's take a look at the video of DeepMind's PPO demo. It looks like this. Okay, this is DeepMind's PPO. That is, you can use the PPO method. You can use this method in reinforcement learning to learn to do some movement or actions. For spider-shaped robots or human-shaped robot, like running, jumping, or stepping over the fence. Okay, the next video is the OpenAI's PPO. It's not as fancy as the previous one. It doesn't have dubbing, but I will dub it. I call this video, "You taking the course, Machine Learning." Okay, I took a course called Machine Learning. But in this course, there are so many obstacles. I kept encountering frustrations. The red ball is the baseline. And the baselines come one after another, which never stop. I train a network for a long time. Then, my collab is offline. The model, after 3 hours of training, disappears. But I still get up and keep moving forward. I want to create a larger model to see if I can train better. But what happened? Out of memory. The circle keeps turning. It just doesn't run. How to do it? But I still get up and keep going. However, for the private set and the public set, the results are different, which really make people feel very angry. This video ends here. It's okay. We still have to give it a positive caption in the end. Even with so many setbacks, I'm still trying to move forward and learn well. This is PPO. Okay, we can just stop here. For the remaining parts, we will talk about them next week. What I have said so far is quite enough for your homework. Okay, thank you all for listening online today. It happened to be almost 6 o'clock.